Hello, class. In this lesson, we're going to talk about types of forces with a focus on balance, but we will get to unbalanced as well. So this is our Unit 1A overview, Objective 3. This is the final objective on our first Unit 1A. So in this lesson, we will be representing forces as vectors. We'll be sketching and interpret free body diagrams. We'll be describing the consequence of Newton's first law, and we won't really be using Newton's second law quantitatively, but I think qualitatively we will. So I'll put like a circle around that. And we're going to identify force pairs in the context of Newton's third law. So pretty much this lesson is the balanced forces aspect. So we won't be using Newton's second law other than saying that when there's no acceleration, there is no net force, and kind of solving because of that. And then using our understanding of Newton's first law to describe motion, also Newton's third law to describe the interaction between objects, so forces and their interactions. So I want to cover the forces that we know. Almost all of these we've done last year. So we have the definition, we have the name, the symbol, and the equation, if any. So we may not have addressed the equation during last year's class, but definitely in the extensions we've done some of that. So name, force between masses. Well, this is going to be between masses. So this is our gravitational. And the symbol is Fg. And our equation, on Earth, it's just going to be mass times gravity. Mass times the acceleration due to gravity. But that g actually comes from somewhere, which eventually we'll learn. So this is actually kind of a open door. We're just trying to stay simple and say we're on Earth, like on the surface of the Earth. All right, a force that one surface exerts on another. So that's like whenever you look at your desk and you have things on it, why is it being supported? And we've called that the normal force, which we're going to call R in this class. If you haven't been using R, you might have been using F of N, but in this class we use R, and R stands for like reactionary force. So when there's an object that's being pulled down by gravity, but the surface is opposing the gravitational force, that's a reactionary force. And we also say reactionary because there's no equation for it. It really depends on how much force is being pushed into the surface that the surface needs to push outward due to the structure, right, the molecular structure of the solid. So there's no equation for this. It's dependent on the situation. Force that a string, rope, or cable exerts on an object. This is tension. And I like to just use capital T, although you might see F of T as well. So those will kind of interchange. And similar to the previous one, it is a reactionary force. It depends on what you're trying to pull, how massive it is. Are you trying to swing it around, or are you just pulling straight? So there's no equation for this. Force exerted by a spring, well, that's easy. It's just spring. Or we might say like elastic. Especially when we get to energy, we call it elastic potential energy. But right now we just call it spring. But and I'll use F of S consistently, F of S for that. And this equation, which we did in our extensions, is F equals negative K delta X. And so again, that's in our extension. So we shouldn't have to cover that. But please ask me if you have questions. Force that a surface exerts on another surface to oppose motion. So it's opposing motion. It's not just exerting on the other surface to hold it up. It's to oppose motion. So this is going to be from surface to surface. So this is friction. Let's use. And we'll use two different types of friction. We'll use static friction and dynamic friction. But most commonly, I might do F of F, like force of friction. But I might include F of D, F of S, which I know means spring, but right, depending on the situation, it determines how you'll label it. Let's just call it F of F. And is there an equation? Yes, there is. We should say F of S right here. And this is F is equal to mu times R. There is, though, some like note in static friction. The force of friction is less than or equal to mu times r. In dynamic, it's equal, and it's only equal to static when the static friction is at its maximum. So again, that was in the extensions. Please refer to that for extra help, but I will be covering it next class because that's when it's going to become useful when we need to use this calculation. Force that air exerts on an object to oppose motion, that's air resistance. And I'll commonly do F of just AR. You might also see F of drag, force of drag, force of friction. You could also call it friction because it's opposing the motion. And this is also dependent. But one thing to know is we don't have an equation, but we do have a relationship, and that the force of air resistance is proportional to the velocity of the object traveling through that air. Side note, at high enough speeds, it's actually proportional to the square of the velocity, but that's due to some the aerodynamic forces at play and the way that air moves around. But for our class, let's just say that it's proportional to velocity because we really won't be dealing with high enough speeds to produce the proportional to the square of the velocity. Force between charges, well, these are charges like protons and electrons, so this is our electric force. And yep, I'll call it F of E. And there is an equation, but not yet given. I'm not going to give it to you yet because when we get to that topic, then we'll introduce it. Similar to gravitational, there's another equation that's not yet given. Those two are kind of go hand in hand as well. All right, so the Newton's laws that we know from last year, Newton's first law, Newton's second law, we hammered this into you last year, so I'm not really concerned about this. An object in motion stays in motion unless acted on by an outside force. An acceleration of the object is proportional to the force acted on it and inversely proportional to the mass of the object. This is really just saying the acceleration is equal to force divided by mass, or more commonly, we'll just see it as F equals ma, and that is what's shown in your data booklet. Right here. That's in your data booklet. So what kind of forces, or how do they look? And so we have, right, we have a normal force right here, right, and we have weight. This is sometimes force of gravity will also be called capital W for weight. You have your frictional force. In this case, you have, if I were to draw a tension force going upward, then that's your tension force, right, or F of T. You have a spring force right here, so it must be pushing upwards, so spring force right there. We have a buoyant force. I haven't mentioned that. This is your buoyant force. And just know that, things float for a reason. It has to do with densities, and when you put an object in water, no matter how massive it is, there's always a buoyant force. Just is it greater or equal or less than its mass, force of gravity pulling downward. And then we have drag force right here. And again, you can see like there's V is equal to 0, let's say. V is greater than 0. And let's say this is like much greater than 0 because the drag force is, the drag force isn't greater. So we just need to say V is greater than 0 in there. And then we need to talk about net force and equilibrium, right? So when something is in equilibrium, and really this is also translational equilibrium. You'll see that word, translational equilibrium. It just means equilibrium. That means the net force is equal to 0. Therefore, acceleration is equal to 0. And we have 3 examples. In this first example, we have the normal force is equal to the weight or the force of gravity. In this next example, there's a tension force, right? There's a cable going upward, and we've added a tension force. Now, we've said that both the tension force and the normal force are both reactionary. So you can see as we added tension force to the system, that the reactionary force, the normal force, decreased. And so these two, T plus R, right, when you add those two together, that should equal your weight. You notice that the normal force decreased when some of its force was taken by the tension force. And even though, so in all these cases we have net force equals 0, except for this one. So in this one, the net force, this is different than the rest. That force is greater than 0, so there is an acceleration. It's greater than 0. And in this case, t is greater than w. We might remind ourselves of the spring force again, that there is some equilibrium point that a spring has, and whenever a mass gets pulled or hangs on the spring, then, or is sitting on the spring, then it produces a force on the spring. And in order for the spring to become a new equilibrium, we need to make sure that the net force is 0. And so in this case, F of G is equal to the spring force, which we know what the spring force is, right? K delta X. And so depending on how far this stretches downward, it tells you how strong the spring is, depending on the mass hanging on it. So like in this case, like in part B, like K of B is going to be less or greater than K of C. Let's look at that in a situation using a simulation. So give me a second, I'm going to open that up. So here's what I'm referring to. You have a spring that has a natural length right there, and you could even include a ruler. And when we add a mass to it, it hangs at a new equilibrium position, which means the downward force is equal to the upward force, and it's in equilibrium. If we were to increase the spring constant, then imagine what would happen. And we can do that, and it becomes stronger. That means it doesn't require as much vertical distance to create a spring force that is equal to the gravitational force. I could also increase my mass. If I increase my mass, it's kind of obvious, right? The gravitational force is going to increase. So therefore, the spring needs to extend a further distance to exert an upward force equal to that new, larger gravitational force. And so this is how it works using that equation F equals K delta X. The negative is there simply to state that the force is opposing the direction of displacement. So there must be a force acting upward to oppose this gravitational force that's acting downward. And since the displacement is down from its original position, that the force must be upward, and that's where the negative is telling us the force is opposing the direction of the displacement. Let's go back to our notes. So we're back on our notes, and I moved to this question: can an object be moving and still in equilibrium? Well, we know when the velocity is 0 and acceleration is 0, then we have a net force of 0, so we're in equilibrium, so check. What about if it's moving? What if it's like 5 meters per second? Well, it really only depends on if it's moving at a constant speed or not. If it's moving at a constant speed, then the acceleration is 0 and the net force is 0, and yes, we can, but only at constant velocity. And that constant velocity is either 0 or 5, right? All right, now we're going to look at Newton's third law with a focus on force pairs. So we know that in Newton's third law, for every action, there's an equal and opposite reaction. So for every force, there's an equal and opposite force. So this is Newton's third law. So we have a fist hits the wall, and the wall hits the fist. The head bumps the ball, right? The ball bumps head. The bat hits the ball hits the bat. Hand touches nose, nose touches hand. So each of these forces acting against one another is producing an equal and opposite force against the other one. That's why, you know, headbutting in football, it can hurt your head. That's why the bat jiggles, like I think we did this last year, jiggles a little bit when the ball hits it, and it deforms a little bit. And these are called force pairs. And so I really want to go into some more depth on force pairs because I don't think we did that well last year. So let's look at this person who's sitting on a couch, or this is like more like a beanbag couch. I'll just call it a bag. And that bag is on the ground. So if I were to ask you to draw a free body diagram of some person, and let's make them just a circle, you might say, well, there's an upward force, that's like our normal force, and there is a downward force that's equal and opposite, and that's our gravitational force. And we'd say, that's it, problem solved. But actually there's some issues with this, and that's because these two are not force pairs, right? These are not force pairs. Force pairs occur like what we saw above. The head bumps ball, ball bumps head, hand touches nose, nose touches hand. And in this case, this normal force is coming from the bag on the person, whereas this gravitational force is the earth on person. So you can imagine we need person on bag and person on earth, and that's exactly right. So we need to make one more for the bag. Let's do the bag first. And if we're laying on the bag and we feel a normal force from the bag, then the bag must also produce a normal force, or we will produce a normal force on it. A normal force, all that a normal force is, and these are equal, is a surface to surface touching. So whenever there is any surface to surface interaction, technically it could be considered a normal force. Though we kind of cheat a little bit and say, well, it's applied force or whatever force it could be. All right, so we have our first force pair, and that is the bag on person normal force and the person on bag normal force. But similarly, the bag also has a gravitational force. So let's draw a gravitational force also acting downward. And we don't know the length, doesn't matter too much, but this is our f of g for earth on bag. And so with that earth on bag, we can keep on going because now we have a force of gravity earth on bag and a force of gravity earth on person from the person. So let's draw a earth as well, another circle. And we can kind of come up with these force pairs that are occurring, right? So the earth that is below us should be feeling a force from us as well. This is a force between masses. So I'm going to draw a purple one going upward and equal to this one. And that is the force of gravity from the bag on Earth. And that's a second force pair. And then we have a blue one that connects to the Earth on the person. So we also have an Earth F of G of Earth, sorry, person on Earth. So these are the force. Now, the Earth doesn't move because the Earth is extremely massive compared to the mass of us. So we will all feel the same force that we impose on the Earth. So like I'm pulling on the Earth just as much as it's pulling on me, just because our masses are significantly different. I feel an acceleration downward, and it barely feels an acceleration up towards me. So this, I believe, is our third force pair. Now we end up with some issues here because the bag isn't falling down and the Earth isn't also falling up. So we need to finalize these. There's one more force pair that we haven't drawn. I'll make it red. And in order for the bag to be stationary on the ground, it must be a very large force upward that's equal to the purple and the orange added together. And this, what is this equal to? Well, what is keeping the bag from falling into the Earth? Well, the surface. So we have another normal force, and that normal force is Earth on bag. And that's going to be equal to this one where this is Earth, bag on Earth. And why is it so big? Well, because it's not just lifting the bag up or holding the bag up, it's also holding us as people up. So the bag is kind of taking the brunt of that normal force the Earth is pushing up against the bag because we're sitting on it. Now, I've kind of made some mistakes with how long these should be equal. So they should all have different lengths, right? Technically, so we'd be like, okay, there's 3 lines there. Maybe the purple gets 2 lines. The blue we can keep as 1, and then sure, this gets 4 lines to signify that the oranges are equal, the blues are equal, the purples are equal, and the reds are equal. So this is our finalized piece of what's actually happening, where the force pairs are. I've separated them by color. Now, the IB will never be too mean on making you actually separate these out, but they might ask you to identify what is a force pair. And you need to just recognize that the force pairs can occur when you can say, well, this is the normal force from a bag on a person, then there must be a normal force for person on bag, and so forth. All right, when we take off from this and actually do some problem solving, it's very similar to last year. This is a very easy unit to move forward on. So I've got a very easy problem to do together. So we need to calculate the mass of the ball and determine the forces acting on the cable in the following pictures. So first, let's determine the forces, because that's the easy one. We have, in this 50 Newton case, a force of gravity acting downward, which is equal to 50 newtons. And since both of these are in equilibrium, there must be an upward force of 50 newtons. Then this is different by only having having 2 cables instead of 1. Now, the one thing that is important to all force vectors is their magnitude, their length is equivalent to the numerical value that it holds. So for example, these are all equal, but to create these 2 wires that are holding up 50 newtons, I know that they will be split in half, and so I must make them half the size. And I know this is 25 newtons, and this is 25 newtons. Oh, I called that F of G. Ooh. You might be like, why did you do that? That's tension. And this might be like T1, this might be like T2. So tension of cable 1 and tension of cable 2. Now I need to calculate the mass. I know that my force of gravity is equal to 50 newtons. I also know that my equation for force of gravity is mass times gravity. So I end up with 50 equals mass times 9.8. And as much as you would like to use 10, know that when we're doing real calculations, we should be using 9.8. So I end up with a mass of 5.1 kilograms. And that's it. All right, I'll see you in class.